Welcome back. I'm truly delighted that we'll be learning integrals thoroughly together. Once more, I sincerely hope you've grasped the previous session's lesson, dedicated time and effort to it, and diligently practiced. Now we're about to delve into the second lesson. Please have your notebooks prepared and let's begin. I stated last session that we cannot integrate terms involving multiplication and division. We tried our utmost to eliminate these products and quotients in the previous session. But the reality is sometimes they simply cannot be removed, so we must find an alternative solution for those instances where multiplication and division cannot be eliminated. The method that we are going to learn today, and it is a very, very important method. It's the method of variable substitution. This means we take a specific part of the expression and we consider it as a new variable. We will give it a name. In fact, we'll simply call it u. And then we rewrite the entire integral completely in terms of this new variable u. The most important thing is that finding u actually requires experience. But there are some parts where we can predict what their u is. However, to be precisely sure that we've identified all the u's, no. Finding u truly requires experience, and we'll try to build that experience by solving various examples. Let's solve a few examples together. In these examples, I'll try to show you these more clearly. The first problem we're going to solve is the integral of x dx over the square root of x squared minus 1. Now look, what exactly is the issue here? How can I possibly eliminate this multiplication and division? This doesn't resemble any of the question models we discussed in our last class. And in this situation, we cannot get rid of this radical and this fraction. We're going to consider a part of the expression as u. What is u? It's something that if I take its derivative, or to be more precise, if I take its differential, it should already be present in the problem statement. Now, I just used the phrase take its differential. Right here, I really need to give a quick small explanation. Actually, this d that we are seeing here is in fact a symbol representing the differential. We take the differential of whatever quantity or expression we designate as u. So what exactly does the term differential actually mean? A differential simply means the derivative of that particular expression multiplied by dx. If the expression is in terms of x, if it's in terms of u, we'll call it du. And if it's in terms of t, we say dt. And if it's in terms of x, we say dx. I'll explain this concept much better when we work through the examples. Let's take a look at our very first example together. Consider the integral of x dx divided by the square root of x squared minus 1. What should we choose for u so that we can find its derivative or differential in the numerator of the problem? I'm going to take the expression under the radical and call it u. Remember that in more complex problems, you might be forced to change your variable multiple times, and that's perfectly fine. You'll understand through experience which variable choice is better. In this question, because the expression is under the radical sign, we're going to consider x squared minus 1 as u. All right, if x squared minus 1 is u, then I'm going to take what's called the derivative or differential of both sides. The derivative of x squared minus 1 will be 2x dx, this dx that we put right after it. It means that we have performed the operation of taking the differential. So 2x dx is now equal to the differential of u, which is du. So what exactly am I looking for now? I'm aiming to ensure that no trace of x remains in the numerator of my question. This means I want to rewrite the entire expression completely in terms of u. In other words, there absolutely shouldn't be any x left. Let's observe together. In the numerator of the fraction, we had x dx. How do I make this x dx be in terms of u? Well, we saw that 2x dx is equal to du. So what does x dx become then? It becomes 1/2 du. So in the numerator, instead of x dx, I'm going to write 1/2 du. And in my denominator, since I had substituted x squared minus 1 with u, it becomes the square root of u. What did we end up with in the numerator and in the denominator? Excellent, well done. The square root of u. Now let's see what exactly happened here. I'm going to write down the square root of u. I'll take u to the power of 1/2 and move it up to the numerator, which means it then becomes u to the power of negative 1/2. Remember, there was a 1/2 coefficient in the numerator with it. The model from our very first lesson, I mean a complex problem that I truly couldn't solve just with multiplication and division. I simply transformed it into the exact model from our very first lesson. It then became 1/2 times the integral of u raised to the power of negative 1/2. Add 1 to the power and divide by the new exponent. You can see it came out so beautifully and perfectly neat. It simply became the square root of u. You might ask, teacher, do I get the full score right here? Rest assured you have truly and completely solved the problem. But just to ensure that your mind is completely at ease, even those really strict professors won't have a single thing to say. Now, instead of the u that we mentioned, just substitute x squared minus 1 and then you're all done. The square root of x squared minus 1 plus c. What seemed like something that couldn't be simplified or separated by division, I solved it quite easily using a simple variable substitution. Let me work through one more example and then I'll give you some time to solve it yourselves. All right, let's move on and take a look at the next example now. So the integral of 2x squared sine x cubed minus 4 dx. Again, there's multiplication between these terms. I can't eliminate this multiplication. What am I doing? In 90% of trigonometric integrals, we take the argument as u. Now, what is the argument in this problem? It's x cubed minus 4. I'll take x cubed minus 4 as u. We take the differential of both sides. Well done. The differential of x cubed is 3x squared dx, and it equals du. What was our agreement? The entire expression, which involves x, must be entirely in terms of u. Let's go ahead and convert it to u now. All right. As you can see, the term becomes sine u. But what I really needed for the differential was 3x squared. But what did I actually have in a problem? I only had 2x squared. So I simply moved the 2 outside the integral because it wasn't the coefficient I needed. I placed a 3 in front of x squared. Well, I can't just arbitrarily multiply the expression by a 3. As you can see, I wrote its reciprocal right next to it. Specifically, I wrote 1/3. This means I moved the 2 outside, substituted a 3 in its place, and then positioned the reciprocal of 3, that is 1/3, before the integral. The resulting integral became 2/3 of the integral of 3x squared times sine of x cubed minus 4. Now 3x squared dx becomes du, so the integral becomes sine u du, and we also had that 2/3 factor that appeared in front, so we have 2/3 times the integral of sine u du, and as we recall from our very first lesson, that 2/3 simply remains as a constant coefficient. The integral of sine u, as we've already discussed and established, is negative cosine u. We complete the solution this way, just to make sure that the professor won't give us any trouble or find any fault with our answer. In place of u, we will insert the expression that we had previously defined. Next example, I'll guide you through it first, then I'll give you some time to solve it. The integral of sine x divided by the square root of cosine x. Let me mention an important point. We never set just x as u. It simply doesn't make any sense. Setting u equal to x doesn't change anything. It gets us nowhere. We need to choose a meaningful expression for u. So what exactly do we do here? Look at what is underneath the radical sign. It's cosine x. I will take the expression inside the radical as my u. I am going to set u equal to cosine x. Well, if we let u be cosine x, then its differential, which is negative sine x dx, will be du. Now, what exactly do I need here? I need to have negative sine x dx. But what do I observe in the problem statement? I'm seeing sine x dx. It's missing a negative sign. I'll put one in the numerator and another one outside the integral to balance it. Now du is correctly formed. So inside the integral, the numerator is negative sine x, and we have the square root of cosine x in the denominator with a negative sign waiting outside of integral. All right, now substitute u. It became the negative integral of du over the square root of u. Since the square root is in the denominator, this becomes u to the power of negative 1/2. Then, by applying the rules of integration, I very easily found the result. It became negative 2 times the square root of u plus c. I was supposed to give you time to solve this, but I ended up solving almost all of it myself. Next time, I promise we'll give you a chance to solve it. Integral of x times the square root of x minus 5. The substitution is x minus 5 equals u. I'll give you a moment, so please pay close attention. You are to set x minus 5 as u. You must express dx in terms of du. Absolutely no trace of x should remain in the final expression. Make sure to substitute everything so that the entire expression is solely in terms of u. Please pause the video here, solve this problem, and then come back. Well, I truly hope you were able to solve this problem. And if you weren't able to, that's absolutely no problem at all. Here we are practicing together to really improve our overall mastery. If you take x minus 5 as u, then dx becomes du. Up to this point, everything is fine, but suddenly you see an x outside the radical, which seems problematic. So what do? What was our agreement? Wasn't there an agreement that the x's would also be eliminated? Well, didn't we take x minus 5 and set it equal to u? You could have substituted u plus 5 in place of x. That way, all the x's would completely disappear. So the question became an integral. Instead of x, I wrote u plus 5. This transformed the expression into the integral of u plus 5 times the square root of u. I had already taught you right in the very first lesson how to get rid of this multiplication. We just need to write the square root of u. If we multiply u to the power of 1/2 into the entire expression within the parentheses, it becomes u times the square root of u plus 5 times the square root of u. As we previously mentioned, if we write the square root of u as u to the power of 1/2, then the entire expression will simplify to u to the power of 3/2 plus 5 times u to the power of 1/2. There's nothing left for it to do here. We add 1 to the power, divide by that new power, and move on. I think many of you have solved it. For those who haven't, that's perfectly fine. Let's move to the next question. We had the integral of x dx divided by x minus 1, all raised to the power of 100. Everyone tell me, what exactly should we choose to be our u? Excellent. It's the expression that's directly underneath the exponent. So we're going to set x minus 1 as our u variable. Be very careful not to include the power itself. Just take what's inside the parentheses as u. Just take x minus 1. Now everyone, please go ahead and solve this problem, then come back here again. Excellent, almost everyone has managed to solve this problem now. If we take x minus 1 as u, its derivative will be dx equals du. That's what the differential becomes. There was supposed to be no trace of x, so if x minus 1 is equal to u, as you yourself have written, then x will be u plus 1. I substituted this into the integral u plus 1 divided by u to the power of 100 du. This fractional form is supposed to be eliminated, so u to the power of 100 in the denominator becomes u to the power of negative 100 and moves to the numerator. It is multiplied, the addition and subtraction are performed, and finally what remains is u to the negative 98 over negative 98 plus u to the negative 99 over negative 99. If you like, you can make it look nicer by moving the negative power to the denominator and simplifying it. Very good. Let's move on to the next example. I want to give you a trigonometry problem. The integral of sine of square root x over square root x. What should we take as u here? Excellent. The general rule in trigonometry, or in most cases, is that if we take the argument of the function as u, the problem will be solved. Okay, let u be the square root of x. Its derivative, or rather its differential, is dx over 2 times the square root of x. But in our problem, we have dx over the square root of x, meaning the denominator doesn't have a 2. No problem at all. We'll just put the 2 in the denominator. We can't just change the problem statement like that. We'll also put a 2 in front of the integral to maintain its balance. So the problem became sine of the square root of x multiplied by dx over 2 times the square root of x. What do we call dx over 2 times the square root of x? We call it du. And with the 2 in front, it becomes 2 times the integral of sin u du. The integral of sine u du becomes negative cosine u. Don't forget the 2. And then simply substitute u with the square root of x. Let's take it up another level. The integral of the natural logarithm of x over x dx. The setup is still in place. Derivatives of natural log and e should have been practiced very well, especially by new students, so that we wouldn't encounter any problems in these sections. What should we consider as u? What options do we have? We have an x, but I told you we never take just x as u. What's left is the natural log of x. Let everyone take the natural log of x as u. Let's see how we can solve this. All right, excellent. You have taken the natural log of x. The derivative, as we said, is the derivative of the argument divided by the argument itself. So the differential becomes dx over x, which is equal to du. It becomes the integral of u du. Now u to the power of 1 plus 1 divided by 1 plus 1. And from here on, you're all masters. Let's move on to the next question. We need the integral of cosine cubed x times sine x. We are gradually starting to raise the bar on the questions, and your level has definitely improved along with me. If you're still encountering difficulties, please pause and go back to the earlier questions, because from this point forward, we intend to elevate the complexity. The questions will become a little more substantial. Let's proceed and see what we have. Here is the integral of cosine cubed x multiplied by sine x dx. The argument here is just x, and we've always been told not to set x as u. What else remains? I see a cosine raised to a power and a standalone sine. I remember that the base of a power is a good candidate for substitution. So in this case, we'll take cosine as u. If we let u be cosine x, then the differential du will be negative sin x dx. I will be happy. Why will I be happy? Because I see the sin x dx. The moment I see sin x dx, I feel a sense of relief. It means the substitution is working. It's only missing one small thing, a negative sign. And adding that is precisely our specialty. I'm going to place a negative sign outside and another one inside to balance it. So the result is the negative integral of cosine cubed x multiplied by negative sin x dx. The negative sin x and dx are absorbed into the u. So what are we left with? Just the cosine cubed. Since we define cosine as u, it becomes u cubed. And there is a negative sign in front of the integral. Don't forget this negative. Or it might turn into a negative mark on your exam. So we have the negative integral of u cubed du. Now just add 1 to the power. You're all masters at this by now. What have we learned so far? Let's quickly review. I told you folks, we don't have a product rule or a quotient rule for integrals. As much as possible, we try to eliminate multiplication and division first, but if that's not possible, we turn to the substitution method. In this method, we select an expression as u such that we can find its differential already inside the problem, or we can easily construct it. And as we said, this requires practice, but usually the expression under a power inside a radical in the denominator or the argument of a trigonometric function, that is our u. Let's continue. In this next question, something interesting happens. Let's take a look together. It asks for the integral of dx divided by the square root of x plus x times the square root of x. There are certain questions where the designer intentionally conceals the pattern. Spotting this comes down exclusively to the sheer number of problems we've practiced. In this particular problem, as I mentioned, I won't start by simply picking a u. It asks for the integral of dx divided by the square root of x plus x times the square root of x. There are certain questions where the designer intentionally conceals the pattern. Spotting this comes down exclusively to the sheer number of problems we've practiced. In this particular problem, as I mentioned, I won't start by simply picking a u immediately. Okay, if I let u equal 1 plus the square root of x, its derivative becomes dx over 2 times the square root of x. Do you recall that I factored out an x from inside the radical? We used the property that the square root of a product can be separated. This is why I split it into 2 radicals. The denominator was missing a 2. I placed the 2 there and balanced it with a 2 in the numerator. Now look at what is under the radical, 1 plus the square root of x. We have the 1 over 2 root x inside and the 2 in front of the integral to balance it. Now let's rewrite it in terms of u. 1 plus root x was our u, and dx over 2 root x became deu, and the 2 is still in front. So it transformed into 2 times the integral of u to the power of negative 1/2 du. So we simply add 1 to the power. I'll repeat this point. In some problems, the substitution isn't immediately visible. You have to reveal it by factoring and separating the terms. Now let's move on to the next example. We have the integral of sine 2x divided by the quantity 3 cosine squared x plus 2 sine squared x, all squared. Since I want you to solve it yourself, I'll give you a hint to start. We know that sine squared plus cosine squared equals 1. We have 3 cosine squared plus 2 sine squared. It's very simple. We combine 2 of the cosine squareds with the 2 sine squareds to get the number 2. And just 1 cosine squared remains. Let's begin by applying this idea. You'll need to split the 3 cosine squared in 2. 2 cosine squared plus 1 cosine squared. Then try to set this entire resulting expression as your new variable. If you manage to do it, that's excellent. If not, no problem. We'll go through it together. So instead of writing 2 cosine squared plus 2 sine squared, we simply write 2. So 1 cosine squared remained. The expression became 2 plus cosine squared, all squared. Now, following our usual strategy, we'll choose the base of the power as u. That means we set u equal to 2 plus cosine squared, the part inside the parentheses in the denominator. Now, let's take the differential. The derivative of 2 is 0. Now, for the derivative of cosine squared, if you remember correctly, when we differentiate, we bring the exponent to the front and then subtract 1 from the power. Then we multiply by the derivative of the base. Since the base is cosine, its derivative is negative sine. So initially we get negative 2 sine x cosine x. As we mentioned in our notes, 2 sine x cosine x is equivalent to sine 2x. So the final differential du becomes negative sine 2x dx. It's missing a negative sign to match the differential. So I'll place a negative sign in the numerator and balance it with another one outside. Thus, the integral transforms into the negative integral of u to the power of negative 2 du. And then, as per our agreement, we simply add 1 to the exponent and divide by that new number. Let's take a look at the next example. The integral of 3 sin 2x multiplied by cosine to the power of 5x. This represents a specific model of questions. In this type, notice the difference. One function has a power while the other does not. The general strategy here is this. When you have sine and cosine, leave the term without an exponent aside. Instead, define your variable u as the base of the expression raised to the power. So what does this look like in practice? First, we have a coefficient of 3. Let's simply move that outside the integral. We've handled this sine 2x situation several times before. So instead of sine 2x, I'm going to write 2 sine x cosine x. This term is then multiplied by cosine to the power of 5x. So let's see. What will the resulting expression look like? The 3 was a coefficient, and we moved the 2 to the front as well. So we get 6 times the integral of sin x times cosine to the power of 6x. Notice that the cosine combine. Now look, one term has a power and the other doesn't. What is the base of the power? It's cosine. Excellent. We set that as u and we leave the term next to it untouched. If this term had a power, it would be more complex. For now, let's focus on our first model, where one function has a power and the other does not. So I'll take cosine x as u. As agreed, after setting u, the differential becomes negative sin x dx. Excellent. Now, let's see what we have here. We're missing a negative sign. So we place a negative inside to form the du and balance it with a negative outside. Therefore, it becomes negative 6 times the integral of u to the power of 6 du. So, we applied the rule u to the power of n plus 1 over n plus 1. The solution was found very easily. This is a crucial type of problem. If you didn't fully understand it, please pause the video and try solving it on your own a few times. Alright, we have the integral of sine squared x multiplied by cosine cubed x dx. Notice that this time both terms have powers. So, what is the general approach for solving this type of question? In trigonometric expressions where one term has an even power and the other has an odd power, the rule is clear. Leave the even power alone. Focus on the odd power and pull out, or separate, just one factor from it. This single factor is reserved for the differential. The remaining part, which is now an even power, will then be transformed to match our variable. Let's look at sine squared x times cosine cubed x. We keep sine squared as it is. For cosine cubed, we split it into cosine squared multiplied by a single cosine x. Now, I am going to take that cosine squared term, the one remaining from the split, and rewrite it as 1 minus sine squared. Remember, it is this remaining part that gets transformed, not the original sine squared term. Do not touch that original sine squared. I replaced cosine squared with 1 minus sine squared. So what do we have now? Now we have sines with powers and a cosine without 1. Remember the rule, if one has a power and the other doesn't, which is u, exactly, the one with the power. So I'll set u equal to sin x. If u is sine x, the differential is cosine x dx, so cosine x dx is exactly du. Excellent, you can see it now, the cosine x dx term at the end of the integral. All signs become u. Cosine x dx becomes du. Let's substitute. It becomes the integral of u squared minus u to the 4th du. Now u squared becomes u cubed over 3, and u to the 4th becomes u to the 5th over 5. The integral of cosine cubed x dx. Now look at the title. One has a power, the other is missing. That is okay, but the power is odd. What was our agreement supposed to be? We needed to factor out a power of 1 from it. So for cosine cubed x, it becomes cosine squared x multiplied by cosine x. Okay, so I am going to rewrite this as 1 minus sin squared x. Now we have one term that has a power and another one that does not. So I will choose the one with the power to be our u, which is sine x. Sine x is u and cosine x dx is du, which then became the integral of 1 minus u squared du, and that integrated to u minus u cubed over 3. The next example is now your turn. The integral of sine to the 5th power of x times cosine to the 4th power of x. This is a very good problem to help you improve your computational skills. In this question, one term has an odd power and the other one has an even power. I will explain the first part, then you should pause. Solve as much as you possibly can, then we will come back and check it together. For the integral of sine to the 5th power of x times cosine to the 4th power of x. Which one did I say we should focus on? That's right, the odd power. So we remove a sine x from sine to the 5th. Now go ahead and rewrite sine to the 4th x using the first identity. You need to convert it to 1 minus cosine squared x all squared. Come on, let's work through this together. Well, I am really glad that most of you managed to solve this question. I want to emphasize again, if you did not succeed, that is perfectly all right. We will go over these topics again through practice exercises, and I will help you gradually master this material. Now let's see what we have done. So instead of sine to the 5th power of x, because sine had a power of 5, you separated it into sine to the 4th x times sine x. Instead of sine to the 4th x, you wrote 1 minus cosine squared x. Since the original power was 4, it was placed in parentheses and squared, right? Well, up to this point where we performed algebraic operations, nothing strange has happened. Now let's check which factor has the power. Cosine x has. So I said cosine x is u, and not concerned with that sine x term at all. Now if we take the derivative, the differential du becomes negative sine x dx. Now in the problem, I will substitute u for every cosine x I see, and for negative sine x dx, I will put du. In the previous step, since we do not have the negative sign, I will add 1 myself, a negative right in front of the integral. Now the expression has been written in terms of u. The negative integral of u to the 4th power minus 2u to the 6th power plus u to the 8th power du. Well done. To all of you who have come this far, you have certainly made significant progress. You can now successfully add 1 to the exponent. And put the power in the denominator, that's clear. Remember, in trigonometric integrals, where one power is even and one is odd, we subtract 1 from the odd power, then we handle the rest. Okay, another example. This is important. So let's solve it together. We have the 7th root of cosine to the 5th x in the denominator and sine cubed x in the numerator. What should we do first? All right, excellent. Let's continue. Because sine cubed x has an odd exponent, we will separate 1 sin x and write sine squared x for the rest. Good. 1 minus cosine squared x. As per our previous agreement, which term has the power? Cosine x. Therefore, we will use cosine x as u. So negative sine x dx becomes du. I will give you a chance to work it out. I really want everyone to get the correct answer. Do not rush. Be a little meticulous with these first few questions. Let's get the right answer. Go ahead and solve this together. That's absolutely excellent. Well done. You can see your calculation speed has improved so much. You are finding the relationships much more easily now. Together, we will substitute u. In the integral, we have taken cosine x as u and negative sine x dx as du. If you substitute for du, it becomes the negative integral of the quantity 1 minus u squared multiplied by u to the power of negative 5/7. We then distribute this into the parentheses to eliminate the multiplication. And now, according to the rules we have previously learned, u raised to the power of 1 more, all divided by that same new exponent, and then the integral's answer is very easily obtained. The next question is really interesting and creative. We are using the substitution method here. The integral is 2x minus 1 cubed over x plus 3 to the 5th dx. This is a really interesting model. There is a beautiful, elegant code for solving this problem. What is that code? Here is the code. You can observe that the denominator's degree is 2 units higher than the numerator's. The denominator has a power of 5, while the numerator has a power of 3. Excellent. This type of problem is solved by taking the denominator, reducing its power to 3, and then separating the remaining 2 terms. So you see, I wrote x plus 3 cubed in the denominator times x plus 3 squared. And you know that in multiplication, we can easily split the expression into 2 fractions. Well, you recall the laws of exponents from high school. When the exponents are the same, we can write one exponent and divide the bases. This is why I wrote the expression this way. I took 2x minus 1 over x plus 3 and put the entire quantity to the power of 3. Now, what was left outside? Dx over x plus 3 squared. Now, what was our agreement? We take the expression under the power as u. It is 2x minus 1 divided by x plus 3. Now, someone might say, I also see that x plus 3 in the denominator. Yes, but in this problem, if you let the fraction be u, it is solved very easily. If 2x minus 1 over x plus 3 is u, let us take its derivative. You remember the derivative of a fraction, right? We said derivative of the numerator times the denominator minus derivative of the denominator times the numerator. Excellent. All over the denominator squared. Some of the brighter students might use the homographic derivative, the cross multiplication method. So if you recall that method, otherwise use the classic derivative. In any case, the differential of 2x minus 1 over x plus 3 yields 7 over x plus 3 squared dx. I am just missing a factor of 7. So I will place a 7 in the numerator and a 1/7 right outside the integral. Substitute the integral in terms of u. It becomes 1/7 of the integral of u cubed du, and from this point forward it is quite straightforward. It is a very interesting model. What was its characteristic? Its characteristic was that the denominator's power was 2 units greater than the numerator's. What I did was I split the denominator into 2 separate parts. I then separated the numerator based on its equal power. I wrote down the remaining portion right next to it, and then I processed it. Let us proceed to the next model. All right, now take a look. I have brought a question for you here. You can solve this in 2 different ways. This is one of the older question types where they told you exactly what to do. You need to take out one of the odd powers from the numerator and then let the other one be u. Do you remember we have solved 3 or 4 of these before? The second way is similar to the last question. This problem can be solved in 2 ways. You can choose. But since I have done fewer examples of the previous type, I will solve it for you using the last method. What does that mean? If we look closely, the power of the denominator is 2 units more than the numerators. That is why I want to solve it using this method. I said, what do we do in these kinds of situations? We split the denominator into 2 separate parts. So instead of cosine to the 5th, I wrote the denominator as cosine cubed times cosine squared. I'm going to separate the cosine cubed. At this point, I would like to give you a little bit of time to go ahead and solve this problem yourselves. Phrases that you can unify. Do not be afraid. Just pause. Think about it carefully. Well, kudos to everyone who took the time and thought about it. I did not say kudos to those who just solved it. Solving it is not important. If you did solve it, that is absolutely great. But what is more important to me is that you truly engage with the integral problem, that you really wrestle with it. You have to grapple with it to truly learn. Otherwise, you will not make any significant progress in learning integrals or indeed any part of mathematics. You really need to get involved with it. All right, so let us take a look at what we have done here. We separated them. It became sin to the power of 3 divided by cosine to the power of 3. The exponents were identical. So sin divided by cosine, all of that raised to the power of 3. We remember from childhood that sine divided by cosine is tangent. So what remained? What remained was the integral of tangent cubed times dx over cosine squared. 1 over cosine squared is familiar. What was 1 over cosine squared? Exactly. It became 1 plus tangent squared. If I take tangent as u, what is its derivative? It is 1 plus tangent squared. That matches the differential. Now I perform the substitution. It becomes the integral of u cubed du. That is very easy. It becomes u to the 4th over 4. Absolutely well done. Let's move on to the next example now. All right, so we have the integral of dx divided by the square root of 2x minus x squared. This is one of those hidden u's, a secret substitution. What I mean is I want you to go and really search for that u. I'm not going to give you any hints or clues. You need to figure out this problem completely from start to finish. Think about it carefully. We will be back very soon. But you must try not to come back until you have solved it. And if you cannot, then go and come back in a week's time. But make sure you solve it. Seriously, go and do some research. Do not even bother looking for my solution. Go, and if you truly cannot solve it yourself, find someone else to solve this problem for you. Thank you all for solving this question either by yourselves or with someone's help. Yes, you are right. The idea to solve this question was to make the expression under the radical a perfect square. This is something that students learned in their first year of high school. I have written down the completing the square method for the expression 2x minus x squared. It is 1 minus the quantity of x minus 1 raised to the power of 2. All right, so what exactly do we do next? According to our previous agreement, the expression under the power is named u, so x minus 1 is now u. So dx becomes equal to du. We then perform the substitution, the integral of du over the square root of 1 minus u squared. Yes, this is a direct result from a lesson in the previous section. Du over the square root of 1 minus u squared. By our convention, its integral turns out to be arcsine of u. Let us move on to the next example. Let us now consider Euler's number, also known as E, which we previously stated is 2.7. Naturally, I am sure you all know that the letter E is named in honor of the great master, the esteemed Professor Euler. However, it became known as Napier's number. Euler, out of respect, attributed it to him. Anyway, let us get back to our topic. In the last session, I told you that the derivative of e to the power of u is the derivative of its exponent times itself. I also told you the integral of e to the power of ax plus b was 1 over a times e to the power of ax plus b. Now let us see what we have in this problem. Okay, so we have e to the x and e to the negative x. To get started, I'll give you a hint. Rewrite e to the negative x as 1 over e to the x. Now start finding a common denominator. We'll work through these together. Excellent. If you find the common denominator, it becomes e to the 2x plus 1 all over e to the x. And now it's time outer times outer, inner times inner. Perfect. So it becomes the integral of e to the x all over e to the 2x plus 1. Now everyone asks, what should we pick for u? Excellent. We can definitely let u equal e to the x. But you might say, hey, I want to set the entire denominator as u. That's perfectly fine. Go right ahead. Do you think you can find the derivative? You see, it's not working. So let's change our approach. What should we pick for u? Let's take the term being squared as u. Remember, e to the 2x is actually e to the x, all squared. I'll let u equal e to the x. Now, what is its derivative? Remember, it's the derivative of the exponent times the function itself. Since the derivative of x is just 1, the differential du becomes e to the x dx. Now, let's substitute. What do we have then? The numerator just becomes du, and the denominator is 1 plus u squared. Now, do you recognize this expression? Yes, the integral of du over 1 plus u squared is equal to the arctangent of u. That was a very good question. Let's look at another problem together. The integral of dx over the square root of x plus the square root of x cubed. Again, here u is not obvious. Why? Because if we let u equal the square root of x from the start, we might not be able to easily find the du. But with a clever factorization in the denominator, we can set up our u and du. Let's factor out the square root of x. Remember, the square root of x cubed is actually x times the square root of x. Now recall, what is the differential of the square root of x? We have dx over 2 times the square root of x, which equals du. Now let's substitute, but wait, we are missing a factor of 2. That's not a big deal. We simply put a 2 in the denominator. Then place a 2 outside the integral. You've mastered this by now. Now we substitute. We get 2 times the integral of du over 1 plus u squared. Everything is now ready. This results in 2 times the integral of du over 1 plus u squared, which, as you've often seen, becomes 2 times the arctangent of u. Come with me step by step so your skills can improve. Let's move on to the next example. The integral of dx over 9 plus cosine squared x. This is one of those specific problems where the u substitution is quite cleverly hidden. Now, why is that? Look at the term being squared. You see a cosine function. Okay, so if we let u equal cosine x, its derivative becomes negative sine x. We don't have the necessary terms here to set up our du. These are the types of problems where we must construct du, either by factoring or by multiplying the expression by something. And if you're looking for a truly creative problem, hold on to this one. Go think it over carefully and then come back. But if you feel it's too early to tackle such a complex problem, just follow me to the next examples. We'll have plenty of time to solve this one later. So, the key idea to solve this problem is to factor out cosine squared x from the denominator. You might ask, sir, how were we supposed to figure that out? The answer is Experience, nothing else. Unless you have prior experience with these kinds of problems, you wouldn't know what to factor out. The only way is to have exposure to these questions. Many integrals are not straightforward, so you need that experience and practice to understand the right approach. To solve this, I factor out cosine squared x from the denominator. I assume everyone knows how to factor, so it becomes 9 over cosine squared x plus 1. Now, why did I do this? Because 1 over cosine squared x is secant squared x, which reminds us of the identity. 1 plus tangent squared x. Let's recall the identity. 1 over cosine squared x is equal to 1 plus tangent squared x. We can make excellent use of this property. Now watch closely. Focus only on the term 1 over cosine squared x inside the parentheses. For a moment, ignore the factor on the outside. We have 1 over cosine squared x multiplied by 9, all inside the parentheses, right? Instead of that 1 over cosine squared, we substitute 1 plus tangent squared x. And since it's multiplied by 9, it becomes 9 plus 9 tangent squared x, correct? And don't forget the plus 1 that was already inside the parentheses. Adding them up, 9 plus 1 becomes 10. So what is the final outcome? Now, we have a 1 over cosine squared term on the outside. I'll also write that as 1 plus tangent squared x so that everything becomes consistent. Everything is now expressed in terms of tangent. So what do I do now? I have 10 plus 9 tangent squared x. What exactly is the base term being squared here? You might suggest just tangent. But since we have 9 tangent squared x, let's make it elegant to find the solution quickly. How do I view 9 tangent squared x? I see it as 3 tangent x all squared. So I've rewritten the term. Now let's take 3 tangent x equal to u. Then its differential du becomes 3 times the quantity 1 plus tangent squared x. What are we missing? A 3. So we put a 3 in the numerator and a 1/3 outside. Now what is left? So we have du in the numerator, 10 plus u squared in the denominator, and there's a 1/3 in front of it. What does that look like? Excellent. That is the standard arctangent form. Now, according to our rule, we have 1/3 times what coefficient derived from the 10? Exactly. We treat 10 as a square root of 10, quantity squared. Now, let's recall the rule. Well done. So we get 1 over the square root of 10 times the arctangent of u over the square root of 10. That was a very challenging problem. Hold on to this technique and go solve it yourself a couple of times. Don't just gloss over this one. It was a truly excellent problem. You might even find it on your final exam. All right, let's move on. The next problem is also beautiful. It's one of those questions that makes you wonder, how was I supposed to know that? How were we supposed to know? Experience. Well done. Now let's look at the integral. The quantity tangent x minus cotangent x divided by the quantity tangent x plus cotangent x raised to the power of 9. Look at that high exponent. I suggest we let u be the base term, tangent x plus cotangent x. Now if you take that as u, what will its derivative be? The derivative of tangent is 1 plus tangent squared x. The derivative of cotangent is minus 1 minus cotangent squared x. Notice what happens. The positive 1 and the negative 1 cancel out. So what is the differential? It simplifies to tangent squared x minus cotangent squared x. Many students give up right here saying we don't have it anymore. What is this? They ask, where is u? Where is du? Where am I supposed to get tangent squared minus cotangent squared from? Well, come on, it's not that difficult. Do you see tangent x minus cotangent x in the numerator? What should you do to turn it into tangent squared x minus cotangent squared x? Use the conjugate. Bravo, we multiply by tangent x plus cotangent x. Remember, this multiplication along with the existing dx builds our du. But be careful, we must multiply both the numerator and the denominator. You can't just multiply the numerator. You also have to multiply the denominator at the same time. Then I'll be happy, because now my du becomes very obvious. My numerator became tangent squared x minus cotangent squared x. Now look at the denominator. We had the quantity tangent x plus cotangent x raised to the power of 9. By multiplying by one more factor, we add 1 to the exponent. So the denominator becomes the quantity tangent x plus cotangent x, all raised to the power of 10. Okay, now tangent squared x minus cotangent squared x became our du, and my denominator became u to the power of 10. This was truly a beautiful problem. Let's move on to the next example. We have dx divided by 1 plus the square root of x. Now it's your turn to solve this one. You usually search for a u whose derivative is already present in the problem. So, but here, it might not be visible. We need to get used to situations where we don't see the derivative immediately. You'll need to experiment with it a bit yourself. Grapple with it. See what you should choose for u. Your goal is to convert the x and the dx entirely into terms of u and du. Go on. Let's see what you can do. Don't wait for me, pause the video, don't return until you've solved it. Go, well done. This is a really nice problem. So what do we choose for u? Square root of x. Let's start with that. We said u equal to the square root of x. The differential becomes dx over 2 times root x equals du. Now you might ask, I have u, but what do I do with this messy differential? The key point is that the differential involves the very u we selected. What does that imply? We set u as the square root of x. Its differential is dx over 2 times the square root of x. So that square root term in the denominator is simply u again. So if I let u be equal to the square root of x, then by taking the derivative, we see dx divided by 2 times the square root of x. Since the u is the x over 2 root x, we can use our substitution. We already set u equal to the square root of x. So what does our dx become? By rearranging, it becomes 2u times du. Now, what exactly were we looking for in the original problem? Don't get lost. What exactly were we looking for? We wanted to ensure every single part of our expression was in terms of u. All right, so I've transformed it this way. What could be wrong with that? Dx became 2u times du. Now go ahead and substitute. The numerator where you had dx is now 2u times du. And in the denominator, we have 1 plus u. So what exactly should we do now? I remember a particular thing I had mentioned. What was it? The degree of the numerator must not be the same as the denominators, right? You recall I said this back in lesson 1. So what exactly do I do then? I'll take some action. I'll ensure the numerator and denominator's degrees are not equal. How? Either I use partial fraction decomposition or I simply divide the numerator by the denominator. It's not a problem. In any case, it can be very easily separated. We can write it as 2u plus 2 minus 2, all divided by 1 plus u. Now, for the next part, this is one of those problems where we must rely on our memory. What comes to your mind right now? Imagine you have a fraction with a first degree denominator. Do you remember what I told you about that? Excellent. That's right. When you have a fraction where the denominator is first degree, its integral becomes the natural logarithm of that denominator. Very good. The integral of 2 became 2u, as you can see. The students who got a bit too excited here wrote the integral of 2s to x. No, that's incorrect. What variable are you integrating with respect to? U. So don't get too excited. Don't be so emotional. The integral of 2 is 2u, not 2x. You must use the correct variable here. It was minus 2 over 1 plus u, and as we agreed, this becomes minus 2 times the natural logarithm of 1 plus u. We use the absolute value here to make the presentation look neater. Let's proceed to the next example. This is another type of problem we'll encounter quite frequently. The integral of tangent x. We haven't actually integrated a standalone tangent before. It's interesting. We haven't come across this before. We're bringing it up because we'll encounter it again in other problems. The integral of tangent x dx. I'm going to write tangent as sine over cosine. Now, what do we have? We have a sine in the numerator and a cosine in the denominator. Even if we just pick one randomly, the answer will still come out. Let's take cosine x as u. You might say, I'll take the numerator as u. Go ahead and try it. See if you get the answer or not. So what should we do then? I'll take the cosine in the denominator as u. If I let u be the cosine in the denominator, then negative sine x dx becomes du. So in the numerator, we have sine x dx. There's no negative sign present. Well, you'll just add a negative sign. One in the numerator and one outside the integral. Based on our prior understanding, it became negative integral of du over u. Surely, there's no one who doesn't know what du over u is. You all know this already, don't you? Du over u becomes e ln u, and since it has a negative, it's negative e ln u. We must memorize this integral's result. This is very important. The integral of tangent x is equal to negative natural logarithm of the absolute value of cosine x. If you carry out this exact same proof for cotangent, you will find that it becomes the natural logarithm of sine x, or more precisely, the natural logarithm of the absolute value of sine x. The derivation is exactly the same. And I want to tell you about the integral of secant right here, right now. The integral of secant is also a particularly interesting integral to consider. Later, I'll also mention another method. The integral of secant is actually quite interesting because it can be solved in 3 distinct ways. There's a creative approach that can be solved using the knowledge we've acquired up to this point. I'd like us to look here and observe that the key trick for the second integral is this. You need to multiply and then divide the entire expression by secant x plus tangent x. How do we know? I said this is a creative trick. You can't just know this without practice. We multiply secant by secant plus tangent in both the numerator and denominator. Now I'll take secant plus tangent as our u. So, if you recall, at the end of lesson 1, I told you about the derivative of secant. What is the derivative of secant? It's secant times tangent. And what about the derivative of tangent? 1 plus tangent squared. So it became secant tangent plus 1 plus tangent squared, which equals du. I had also mentioned to you that 1 plus tangent squared is equivalent to 1 over cosine squared, and 1 over cosine squared in turn means secant squared. So what did our du ultimately become? It became secant tangent plus secant squared, all times dx. If we factor out a secant, we get secant x times secant plus tangent all times dx. This whole part is our du. Now look at the fraction. Wasn't that the numerator of the entire fraction? Secant x times secant plus tangent. So what did we call this? du. So the numerator became du. What was the denominator, do you remember? Secant plus tangent. And what was it called? U. Okay then, so we have du over u. What does that become? The natural logarithm of u. What exactly did you consider u to be? Secant of x plus tangent of x. So the integral of secant x dx becomes the natural logarithm of secant x plus tangent x. If you're someone who solves many different kinds of problems, it's not a bad idea to memorize this. All right, let's move on. And the integral of dx divided by the square root of a to the power of 2x minus 1. I've chosen this as the final question for you. It's the last question of lesson 2. No, this isn't the last question you'll solve. You'll still be solving questions for a long time. But the final question we want to look at together in this section is this: the integral of dx over the square root of e to the 2x minus 1. Again, it's one of those questions where the u substitution isn't obvious. I want you to take your time, solve it yourself, and then we'll solve it together. The question, I believe, has a couple of methods. I solve it with this method. You might have solved it a different way. I said that with integrals we might arrive at the answer through different approaches, and the best way you make sure our solution is truly correct or not is to take the derivative of the answer we have obtained. Let us take a look together. I started by factoring out e to the power of 2x from underneath the radical sign. Now e to the power of 2x, that means it is a perfect square. So when I factor it out, what comes out from under the square root? Excellent. The power of 2 cancels out, it becomes e to the power of x. What did we get under the radical sign? 1 minus 1 over e to the power of 2x. Remember that e to the power of 2x is equivalent to e to the power of x, then squared. I've written it in exactly that form. E to the power of x all squared. And since we know there is a 1 in the numerator, that one can be brought inside the power. So it became 1 over e to the power of x all squared. I see an expression that is under an exponent. What was our rule? We were supposed to take that term as u. We took 1 over e to the power of x. U, that is right. Then we took its derivative. Everyone knows the derivative of a fraction. I emphasize, if you do not remember it, please go and review it. We took the differential of 1 over e to the power of x, and it became negative 1 over e to the power of x dx. Now go ahead and substitute it. Negative du over the square root of 1 minus u squared. Remember, this integral becomes arcsine of u. Don't forget that negative sign. That's enough for today. I know these topics were challenging. We will see each other very soon in the next segment. Do not forget. First and foremost, you need to work through all of these exercises multiple times. And then, secondly, math is all.